I am Dr. W.B. Gangule from Kamla Nehru Mahavidyalaya, Nagpur. In my first lecture, we discussed about the electronic spectra and different types of transitions taking place in the metal complexes. And in that also we have discussed about the two selection rule. Number one is a spin selection rule, and number two, Laporte selection rule. And after that, now in today's second lecture, I am going to discuss about the ELS coupling, which is also known as RS or Russell-Saunders splitting. There are some important relations and some important rules to find out the spectroscopic ground state terms. So these ELS coupling are used to determine ground state term symbols for different systems from D1, D2, D3 up to D10. And in the university exam also the question is asking about this ground state term. So in the next slide, here are some important features which is important, and if this feature known to us, then it is possible to find out the ground state terms. So as we know that different types of transitions are taking place, and there are transition from ground state to the exercise state taking place. This is possible, but different type, if the system have more than one electron, then there is a need to discuss the interaction between the electrons. For example, in case of D1 system, D1 means there is only one electron in the valence shell of that system, and therefore there is no any complications during the absorption of energy. But when the system contains more than one electron, then the interaction between the particular electron and other electrons is necessary. We have to consider it, and this consideration can be explained with the help of orbit-orbit coupling, spin-spin coupling, and also spin-orbit coupling. And now there are different types of this splitting, and in which this it is observed that spin-spin splitting or coupling is greater than orbit-orbit splitting, and which is also greater than spin-orbit coupling. It is also known that the element after atomic number 30, spin-orbit coupling become more significant, and therefore with heavy element different systems known as JJ coupling is used. When several electrons are present in the subshell, the energy state obtained depends on the result of the orbital angular momentum, quantum number EL vector, and the spin quantum number S vector of each electron. So now here to determine or to know the ELS coupling, we should have to know the important features. Once who knows these features or important rules of ELS coupling, then it is possible, or we can determine the ground state term symbols. So according to this ELS coupling, so important point is first important point is all EL vectors of electron of the central metal ion coupled together electrostatically to give the resultant vector EL, which is also known as total orbital angular momentum, also known as this quantum number determine the energy state of atom, and different values of EL can be represented by the symbols as we represent SPDF, capital SPDF. If the value of L is 0, S, 1, P, 2, D, 3, F, and so on. And in case of empty half filled or completely filled subshells, value of L, total angular momentum, is 0. Second important point is all vectors of electron coupled together to give the resultant vector capital S, and total, which is also known as total spin quantum number. This quantum number determines spin multiplicity of the atom. So these two important, capital L, capital S. Now third important point is, finally capital L and capital S vector coupled together to give the resultant vector J. This J is nothing but the total inner quantum number, and J can be determined, J is equal to L plus S. Fourth important point is, the quantity 2s plus 1 is also known as the spin multiplicity of the L state, and this multiplicity may be singlet, doublet, triplet, depending upon the value of 2s plus 1. If the 2s plus 1 value is 1, singlet. If the value is 2, doublet, like that. Fifth important point is, there are some permitted values of J. These values varies from L plus S to L minus S. So J have different values between L plus S up to L minus S. So in the next slide, sixth important point is, the possible values of J can be known, or it is 2s plus 1 when L is greater than S, and 2L plus 1 when L is less than S, and when L equal to 0, then the value of J is equals to S. 7th point is how to represent the terms, ground state, term, later. Term symbol for particular configuration is represented as shown here. This is the representation. Here is a term letter, that is S, P, D, M, anyone. Here is a value of J, as we have discussed how to find the value of J, and this is the multiplicity 2s plus 1. Now to find the value of J, there are two important rules are there. Rule number 8. The ground term symbol is selected by following the rule. So here at the A, select the minimum J value, that is L minus S, if the subshell is less than half filled, that is D orbital is there, D over 5 means half filled, less than 5 values is there 5, then it is a less than half filled. So in that case, minimum J value is the ground state term. So we have to know the value, minimum value of J minus S, L minus S, or minimum value of J. So minimum value when the subshell is less than half filled, we have to use this rule number 8. If rule number 9, select maximum J value, that is L plus S, for ground state term if the subshell is more than half filled. So these are the two important rules to determine the ground state term, whether it is half filled is that is the subshell is less than half filled or greater than half filled. As we know from D1 to D10, D1, D2, D3, D4, D4 up to 4, it is less than half filled, and D6, D7, D8 all are up to D10 systems are more than half filled. So by using all these important features and rules, now one table is given here, and now here in case of D1 system, the term letter is D, because for D azimuthal quantum number L is equals to 0 means S, P, D. So value of term symbol is L value is 2 means D. So term letter is D, and multiplicity 2s plus 1. One electron is there, 1 by 2. So formula is 2s plus 1. So put the value here, S spin 1 by 2. 2 to cancel, 1 plus 1, 2. So multiplicity is 2. And term symbol is here now, two term symbols are here. So how to find these two term symbols? I can show here also. Here 2s plus 1 is 2. Now L minus S and L plus 2. L plus S. So when L minus 2, 2 minus 1 by 2. 2, 4 minus 1 by 2, 3 by 2. And here again you can find out by doing L plus S, 5 by 2. So this is the J value. J value obtained from L plus S and L minus S. So two values are there. So 2 is the multiplicity. This is the term later, and 5 by 2 and 3 by 2, two values of J are there. Start from L plus S to L minus S. Now out of these two term later, what is the ground state? Term 2D 3 by 2 as per the rule of ALS coupling. If the subshell is D1, subshell is less than half filled, so minimum value of J is the more stable. So 2D by 3 by 2 is the ground term symbol for D1 system. Similarly, in case of D2 system, the term later is F, because 2 is the L value, L equals to 2, and and orbital angular momentum is 1, vector addition is 3. So term L, capital L equal to 3 means F subshell, and multiplicity is 3, 2s plus 1. Yes, 2 D2 are there, 1 plus half. What is then? Because similar spin is there, so 1 value. So 1 into 2, 2 plus 1, 3. So in this way, again now there are all the values you have to take of J. 3 is the multiplicity, 2s plus 1, and 4, 3, 2 are the values obtained from the values of J, and J value obtained from L plus S up to L minus S, all the values. If you determine, you can find. Now again, out of 3 terms, minimum value of J 3F2 is there, and therefore this is the ground term symbol. So in this way we can determine the values for D3, D4, D5, D6, D7, D8, D9 and D10. In the next slide now, as we know, there are different types of transitions and taking place and promotion of electron from lower to higher energy level, and 3 different terms are there. When we consider the octahedral system, in case of octahedral system, S term does not undergo any splitting, P term also does not undergo any splitting, but as we know that in case of octahedral, D term undergo splitting, and we know in case of octahedral, D orbital undergoes splitting into T2G state and EG. So T2G and EG are the two states in case of octahedral field, and these are the symbols shown here. These are the spectroscopic term S, P, D, F, and now here in case of octahedral field, it is represented A1G, S orbital, F subshell, or S term is A1G. In case of tetra, only A1. In case of P, T1G, and here T1. In case of D, T2G and EG, here only T2 and E. In this way, F also. So these are the terms, symbols used for different spectroscopic term SPDF in case of octahedral and also tetrahedral field. This is one example how the orbital, how the ALS coupling can be used. This is here one example is taken, that is P2. P2 means it is the configuration of carbon. Carbon have atom number 6, 1s2, 2s2 and 2p2. 2p is having 2 electrons. So how we get different values, how we shown here in this slide. So now for P, L value is 1, azimuthal quantum number value is 1, and orbital angular momentum is 1 by 1 into h upon 2 pi. So now by vector addition, these are vector addition diagrams. For P, L equals to 1, L equals to 1. For vector addition, value of L is 2, and L is 2 means this state. Here two additions are here, L equals to 1, L equals to 1. But here resultant value of vector addition is L equals to 1. So the P state. In this way, L state. Here this state L equals to 1, L equals to 1. But opposite because of spin, L is 0, and now L is 0 means S state. This is for orbital angular momentum. Now this is for spin angular momentum. This is the value of L. We obtain capital L value. Here we obtain capital S value. As we know, spin angular momentum, yes, spin of the electron can be plus half or minus half. So here value is shown. These two electrons are there, plus half, plus half. What is resultant is S equals to 1. When here 1 is plus half, minus half. What is then resultant is 0. S equals to 0. So in this way, this is the value of capital L. Value of capital S can be determined, and finally L and S. L equal to 2, S equals to 1. Value of J is 3. So in this way J value can be determined by using this vector addition. So after calculation of this ground state term, also we have to use the Hund's rule, whether which system is more stable. And it is observed there are three important rules of Hund's rule, and this first rule says that we have to use more stable system is that which is having largest S value, and in second rule, for given values of S, state with the highest value of L value is the most stable. In case of third, again if there is an ambiguity, then the S and L, the smaller J value is the most stable, subshell is less than half field, and the biggest J value is the most stable if the subshell is greater than half field. Now after calculations that we have taken the example of carbon P2 state, these are the terms. By using that 3 Hund's rule, these are the configuration for carbon in ground state 1, 2, 3. By applying the first rule, the term 3p state is the ground state as per the rule number 1. By using rule number 2, 1d state correspond to the L equal to 2, therefore most stable is the L equals to 0. So in this way, now as we know, in case of octahedral field, there is no splitting of S, there is no splitting of P, but D can split. But now here carbon splitting is shown here in ground state. S is only 1, D is also only 1 in case of carbon, and P, these are the 3 states, and P undergo 3 splitting, 3p0, 3p1, 3p2. So these are the different energy state in case of this carbon. These are the term symbol used, or ground, we can also say that ground state term in case of octahedral field. For S, already we have seen this. For S, A1G, for P, T1G, for D, F, G, H, we have to use these term symbols. The splitting of energy level, as we know again now that if here is given Auger diagram, but we are discussing in another lecture, not here. Only I am giving how the splitting is taking place in case of octahedral field. Now here are the 5 d orbitals. This is the energy, and this split up into T2G state and AG state. This is the delta 0, delta O octahedral field. This is barycentral. Values are given for this. This is splitting, and these are the terms. This is the A figure, this is for B figure, and this is splitting of F into 3 states, T1G, T2G, A2G in case of octahedral field. And here also given how d orbital T2G into EG state is split up, and this 3. So these are the terms, and diagram can be plotted for different D1 to D10 system. So today we have discussed only the important features of LS coupling, and it is also possible to determine the ground state terms for transition metal ions from D1 to D10 system. So today we stop here, and we will continue in the next lecture. I will give you about the details about the Auger diagram and Tanabe-Sugano diagrams and different diagrams. Okay.